So let's start chucking stuff. Start throwing objects, launching objects, all that fun stuff. We are so I first want to draw your attention to kind of where we ended yesterday. We ended with this slide. We had you highlight it, star it, all that good stuff. It talks about when you're launching an object at an angle. You need 3 pieces of data. Okay, first off, you need to know how fast you're launching the object or what your initial velocity is before gravity takes hold. You need to know at what angle you're launching said object. Okay? And lastly, you need to know at what initial height that you're launching that object. So V sub 0 in here, that's our initial velocity. Theta sub 0, that's our launch angle. And H sub 0 is our initial height. So we'll even use that when we go on, and then we're going to be able to ask some questions when we get in. Okay? So, for those of you that don't know who Big Al is, allow me to introduce you to Alfred Delilah.
Hi, my name's Alfred Delia. At home they call me Big Al, and I hit dingers.
Big Al hits dingers. Okay? So that's from the Little League World Series. They've upped their introduction game for the little kids because it's on the national stage, and so if you only watch one part of the Little League World Series, watch all the intros because they're hilarious. What these kids come up with. Okay, so Big Al hits a ball. We want to know if Big Al's hitting a dinger or not. Okay, so Big Al hits a ball at an angle of 28 degrees with an initial velocity of 75 feet per second at a height of 3.5. Okay. My question to you is, will he hit a home run if the ball follows the left field line where the Little League fence is 190 feet away and 4 feet tall? Okay. So we're actually going to have 2 functions going on here. The first function that we're going to have is going to be the ball. Okay. So we're going to follow the path of the ball. And that parametric function is going to be x equals, my initial velocity was 75 feet per second, times the cosine of 28 degrees, because that's my launch angle, and then that is all times t. I'm following that, the starred, highlighted, whichever one plan that we have. My y value, bless you, is going to be negative 16t squared plus 75 sine of 28 degrees times t plus 3.5. Okay? So let's put that into our calculators. So again, if you're using one of ours, you definitely want to start a new. And so let me double tap on. So turn it on, then on again gets you to this one. You want to start the new. You don't want to save, and then we're going to add a graph. With that graph, we need to change that to a parametric function. So that's menu, graph entry and edit, parametric. Okay. Now we add it into the calculator. So we had 75 times the cosine of 28 degrees times t. Then we had negative 16 t squared plus 75 sine of 28 degrees times t plus 3.5. I'm not too concerned with my t range of values, because if it's not enough seconds, we'll see the ball hanging in midair. If it's too many seconds, we'll see the ball go underground, and I'm just fine with that because we're going to assume that as soon as it hits the ground, it hits the ground. Okay? So when I hit enter on that, I see that. Now the downfall with that is I don't see the entire path of the ball. Okay? So I have to adjust my window. I can adjust my window in one of two ways. I can slide my cursor over here to the number at the end, the number on either which direction I want to go, and I can adjust that number and hit enter, and it will move it. Or I can go into menu, window and zoom, window settings, and I can use some logic. So logic tells me that I need to know if this ball is going to clear a wall 190 feet away. So I should go out to at least 190. I'm going to go out to 250 feet. Oops, tap the brakes. I went in the wrong spot. I did not go down. We're going to stay at negative 10, and then we're going to go out to 250. Okay. I like to see nice, neat, and I want to know what they are, so I'm going to go by tens. Okay. My y's is my vertical, how high that ball is going to go. And so I'm going to say that let's go negative 10 here, because again, I like to see the ground, and I think it's going to go no more than 50 feet in the air. So once I do that, then I click OK. Now I see the ball path, if you will, of the ball. Okay. So that's the ball. And we can trace that, and we can find all these different things. But what we can do now is we can also add in the wall. The wall needs to be 190 feet away. So I'm going to set my X value at 190 feet. Then the wall needs to be 4 feet tall. So I'm going to say that Y here is just T. If I set my Y function as T, then I'm going to need to add in a T range from 0 to 4. Because that will build a wall 4 feet tall. If I went with something different here, I could go with a Y function of 2t. Then my range would go from 0 to 2 to get a 4-foot wall. I could go with t plus 1, and then I would go from negative 1 to positive 3 for my t range. See what I'm doing there? Either way, I'm getting my maximum value of my Y function is 4. Okay? My minimum value is 0. So when we go and we add that function onto our graph, we can hit tab to get the next one, except mine now is acting up again. We can hit tab on the next one, and then we can say 190 feet there. We can say T there, and we can have to change this 6.28 if I leave it at 6.28, the wall that I build is going to be 6.28 feet high. Okay? So we're going to drop that down to 4. And then when I hit enter, there is my wall. Yes, sir.
How do you add the other functions?
Tab.
Oh,
Did Big Al hit a dinger? Nope. Big Al did not hit a dinger on this particular path. Okay? So no dinger on this. Okay? Now, how much harder would he need to hit the ball to actually hit a dinger? So what we can do with that is we can go back in and we can adjust this initial velocity number in both of those equations, and we can see until it gets over the wall, until we hit an actual home run. Okay? So find me the minimum velocity that Big Al would need to hit the ball at to actually hit a dinger. Anybody come up with a number? 86. 86? That's what I got. I got 86 too. So we change that to 86 there. We change this one to 86 there. And now if we zoom in, on that, it just squeaks over the fence at 86. Okay? Okay? Now, what we can do with this, let me go back to this, can I control Z it? There we go, fantastic, I can. Let's go back to, what was our initial one, 75? Okay, so here's our initial one. We have a function on here, and we kind of told you a little bit about it yesterday. I forgot to mention it in my class, but that's all right. I'm over it. We have a function in here called trace. Okay? And what trace allows us to do is it allows us to find, first off, I'm going to set my trace step at 0.05. I'm going to set, just for me, you don't necessarily have to do that, but I'm just going to do that. And then, so if I go into trace now, what that's doing is every 0.05 of a t value, it's giving me the position of the ball. And so I can follow along with that, the ball's path, the motion of the ball, and I can figure out that it goes to a maximum height of approximately 22.9 feet. Would be the maximum height of this ball, of the original ball that Big Al hit. And that happens 1.1 seconds after he contacts the ball. Okay? So that allows us to find that stuff. Because what we're going to be doing later on, in this unit is we're going to be finding this kind of information. Now, I will also tell you that there will be a video posted on Canvas next week. I doubt that I will get to making it today, just because I don't have a room to make it, and all of our rooms are busy the rest of the day. But for sure on Monday, of how to algebraically solve for all of these values, how to algebraically solve for the maximum height of the ball, how to algebraically solve for the distance, and those kind of things. And then I'll also post another one on, again, with the steps on how to do it using the graphing calculator. Okay? So we can find the maximum height of the ball. We can find the distance that the ball hits the ground, how far away it hits the ground. So it hits the ground about 152 feet away from where he hit the ball. So he only hit the ball 152 feet. Okay? It took 2.3 seconds for the ball to hit the ground. We can do all of that. All of those calculations. Okay? All right. So with that being said, what I would like you to do now is I would like to know how far can Aaron Rodgers throw a football if he throws it at an angle of 58 degrees with an initial velocity of 36 feet per second at an initial height of 6 feet. Okay. How far can he throw said football? So I'm looking at an x value of
No, I feel like it would just be the...
Yeah, they're really well college t-shirts, so I could just like...
So I got a maximum height of 20.6 feet. We'll just hit 20.6 feet at 0.95 seconds after he throws it. So about almost a second after he throws it, it's at its maximum height. Yes? I know. And bonus question was then, what is the oh wait, that was maximum height. What did I want to say? How far? Oops, I went the wrong way on that one. So about 40 feet then at 2.1 seconds for that part. So about here would be 40 feet at about 2.1 seconds. So the maximum distance that he throws under these conditions, now can he throw it farther, Zoe? Yes, he's a professional. Okay, whether or not he needs to make $59 million next year or not, he can still probably throw it farther than 40 feet. My old tired arm can throw it 40 feet. Okay?
Probably out for their insurance.
Yeah. Okay. And then the maximum height on the bonus question is that. Okay? Good? Love it. We gave you a homework sheet, pink packet, homework packet that you can start working on over the weekend.